Welcome back again. In the past few weeks, we already talked about the cost strengths approach and the functional approach. And I want to this week talk about basically an approach that combines both of these ideas. So it's using summarization, or in this case, it's rather called tabulation, but of non-distributive analysis. And this approach is called VASCO. And like I said, it's basically combining elements of the cost strengths approach with elements of the functional approach. But what makes it interesting is, like I said, that it can be applied to problems that are not even distributive. And if you recall the cost strengths approach, then it had exactly that advantage, right? That you can apply it also to non-distributive problems that have non-distributive data flow functions. But we saw that it has these disadvantages, right? That you need to bound your analysis to this factor k that constrains the size of the calling context strings. And we also saw that it has this disadvantage that there's no reuse across summaries, that there's no reuse because there are no summaries across equivalent calling contexts. If we recall the functional approach, then it had different trade-offs, right? So that does save repeated computations for similar calling contexts or equivalent calling contexts because it has these summaries, and it's also infinitely context sensitive, but it requires a distributive analysis problem. And the reason for this we saw was that in the functional approach, you're basically computing symbolic procedure summaries, right? So we saw that these flow functions in the callee, they're basically collected into a symbolic expression. You could also say a formula, right? And that needs to be of finite size, so it needs to be reduced, and that can only be done if you have a distributive analysis problem. And the approach that we are going to be talking about today, it departs a little bit from this idea of a symbolic representation of these summaries. It uses a more concrete summary representation. And as it turns out, once you have that, then there's no need anymore for this distributivity. In order to illustrate the approach, let's take a look at this example. So let's assume we want to do constant propagation for this program. And here we are having two caller procedures. So this is a calling context for procedure H, which you see here. And this is another calling context, also calling procedure H. Okay. And let's assume we want to know whether C has a constant value at this print statement and what that constant value is. Now, if you carefully look at this program, you will see that this is again one of these nonlinear expressions here, and we already talked about the fact that these expressions, unfortunately, they are not distributive. So analyzing this precisely is not a distributive problem. And therefore, if you have a distributive framework and you use the general functional approach, then you cannot precisely determine the value of C, because in order to do that, you would need to know the values of A and B, and you would need to be able to compute the plus operation on them, and that is not distributive in this particular setting. But if you have a full constant propagation, that actually yields the value 5 for C here, because if you take a look at this, we have this one calling context here, for instance, right? And if we call this C1, then here you will get a mapping of A equals 3 and B equals 2. And by the way, here we assume that all these variables that you see here, they are global variables, okay? So they are visible in all these 3 different procedures. So there's no need for any parameter mapping here. But yeah, so in context C1, we have this variable mapping here, and therefore, if we do a full constant propagation, a non-distributive one, then we can know that C here has the value 5 for this particular calling context. And if we look at the second calling context, we see that, oh, these two numbers, they're actually flipped, right? So here we have different context information, it's different input values, but nonetheless, because the plus operation is commutative, right? So we also obtain the value 5 here for C. Okay, so that means there is a way, for instance, using the call strings approach to get a precise answer for the constant value of C here. But the problem that we know from the call strings approach is that it is inefficient of handling equivalent contexts. And to illustrate that, let's again take a look at a slightly variant of this example here. So here I've modified G so that it actually computes the same values as F. Okay, so now A is not 2 but 3 and B is 2 and not 3. And so these two contexts, they're actually equivalent, and you can also see that if you compute the call strings approach here, then we will enter C1 with this environment, but we will also enter with C2 and the same environment here. And so we will be doing, again, the same computation, this times twice. We will get a precise answer that C is 5, but we will be wasting some work here, right? So ideally, we would want to have an approach that computes this only once and not twice, but the call strings approach, it doesn't really give us this. So the question is now, can there be an approach that somehow summarizes the effect of such a callee procedure H, and even maybe the effect of partial computations within H, but that stores summaries not symbolically, but with some in some other way, so that we can even store summaries when we have such a non-distributive problem. And the idea behind this approach VASCO is that we use instead summaries expressed through concrete input-output mappings. So that means we are not storing procedure summaries symbolically, but we are actually, we're sort of executing the summaries directly on the input values, and we are only storing the results. And again, considering the example I showed you earlier, we can take a look at what this would look like. So here I'm showing you, first of all, the first calling context F, okay, the same one that we had before, still with the call side C1. And again, the same callee procedure H, that's what you see here. And first, let's take a look at what we have here. So we are starting our constant propagation with some initial information that maps A to 0 and B to 0. And now we are also labeling that particular calling context here. So we are saying that F, when it is evaluated under that initial analysis information, this is an initial context that we call X0, okay? And we are storing that information here. So we are storing in this table the information that X0 is a context in which we evaluate F under this initial entry information here, okay? And now we do this. So this is regular intra-procedural flow function computation. We now know that A is 3 and B is 0. Now we learn that B has actually been updated to 2. And this is the analysis information that we have when we get to this procedure call. And now we process that call. So we actually move into procedure H, which also brings us into a new context. So we are basically now evaluating within that scope. And that means that we will also add a new context to this table down here. In particular, first we will store that we now have a context X1, which regards procedure H, not F, okay? And we have these initial entry values, A equals 3 and B equals 2. We store that in our table, okay? And then we take these input values for context X1, and we are analyzing through the procedure. And now we learn precisely that C actually has value 5 here, it's TLS value 5 down here, and that is actually the environment that we have at the return statement. And because of this, we actually now also store this particular exit value here. Okay, so into the table, once upon reaching the return statement, we store this exit value, this exit environment that tells us, basically how this input value has evolved into this exit value by conducting whatever functionality is expressed by H. And this is basically a summary function, right? So this is telling us, given this particular input environment, what is going to be the output environment if we call H. Okay? But if you look at the summary, this time it's not symbolic, right? So here we are not saying what the function looks like that H computes, right? And in fact, it could have done a much more complex computation than you see here. We now know by looking at H that it's only adding A plus B, but looking at only the summary here, we have no idea whether that's really how C was computed, right? It could have been a much more complex computation. We don't really know that. And that means in some way, this is much more abstract, right? Because it's abstracting away the function that H is actually computing. But in other ways, this is actually also much more concrete, right? Because this is now a summary that is actually restricted to these concrete input values, right? So this is assuming that we have a context that provides us with A equals 3 and B equals 2, then we know that this is going to be the result. But we don't know anything about any other context. Something that we also store along the side, and that's going to become more important later, is such a context transition diagram that tells us if we start in context X and go to context and reach call site C1, then we move into context X1. Okay, and that's really I like the notation because it's very neat and clean, right? It only talks about context and call sites, and it can be that neat and clean because here a context, it comprises both a procedure and these entry environments, right? So when I look at a context X0, I not only know that this is a context of procedure F, but also the concrete valuation of these variables. Okay, and that's why I can simply say, okay, now if I reach C1, I'm gonna move to that other context. Okay, now we have computed that summary information for this context X1, but how does this help us now? So let's again assume that we have this other calling context G, and now we are looking again at the variant that is identical to F, right? So where we would normally, using the call strings approach, have duplicate computation. So again, now we have context G, and it's doing the same as F, so it's assigning 3 to A and 2 to B. So this means as we compute through G, and now we reach this call site C2 that is also calling H, we can do the following. We can take a look at this context table here, and we will see that we already have an entry for calling H under this particular valuation here. Okay, and that is the valuation, the environment that we also have here. Okay, so this matches. We have an entry, a matching entry in these two table columns. And for this particular entry, we already have computed also an exit value, right? So we have that. And then we know that we can therefore also use the very same exit entry directly down here. So we can simply copy that over. There's no additional computation required through H, because for the very same input environment, we have already computed that, and its result has been stored here, it has been memorized here, and it can simply be reused. Okay. So now we can store this here. We can say for the calling context x2, which is g with the initial input valuation, everything 0. That also, gets this return value here. And when I say we can copy this value over here directly, this is only true actually because there's no additional effect here, right? So normally we would take this exit value here and we would plug it in at this program point, and if there were additional computation here, of course that would need to be computed within G, right? But here there is no effect, so you can basically copy this over directly. This then gives us also this context transition diagram that we have here, right? So we have this context x2 now, and here with call site C2, we also get into context x1. And that's important, right? So it's the same context. That's why we can do this reuse, right? We can have it here. If any of these parts of the input here would be different, right, then this would not be applicable anymore. So what's important here is that it uses abstract values as context and not calling context strings. So that's what makes it different from the call strings approach, right? The data flow values, they're not really annotated with calling context strings. They are, through this context transition diagram, implicitly annotated with the call site and with input values, but that's about it. The effect of this is that the same procedure is only analyzed once for the same abstract input values. So if you have two equivalent calling contexts, there's only the need to analyze the callee procedure once, and then you can reuse summaries. We also have this context transition diagram that I showed you, which associates value contexts with call sites. And therefore, it actually allows also for a reconstruction of calling context strings. So I didn't talk about this much, but basically because call sites are encoded in this context transition diagram, you can use that to reconstruct all possible calling context strings if you want to. But so far, that wasn't really necessary. After a short break, though, I will show you an extended example where we use the VASCO approach using constant propagation with a combined pointer analysis. And here, for ease of exposition, I will actually use a C-like language. There you will see why these context transition diagrams are actually a very nice and useful representation as well. Speak to you soon.